Good morning, everybody. Thank you very much for the invitation to talk to you today about um, ex situ lift out, cryogenic ex situ lift out for manipulation of cryofib TEM specimens. For those that don't know me, my name is Lucille Giannuzzi. I'm president of Expresso LLC. And just a little bit of um, history, where we are, who we are. So we are located in Southwest Florida. We're a small company. I actually spun this off of my consulting company over 10 years ago now. And so we have a facility here that we can build systems as well as demo systems. As so, and we have over 30 systems worldwide. Most are in the U.S. Some are in Asia and Europe. These are what I would refer to as ambient systems. So far, we actually just got our first order for a cryo system this week, so we're really excited about that. So I'm going to start by explaining to you what ex situ lift out is, or the acronym EXLO, for fib specimen preparation. This was developed in the mid to late 90s for fib specimen prep, focused ion beam specimen prep. And it's a way to remove samples, fib prepared samples, from their trenches outside of a fib. And this was described very early on, again in the mid 90s to early 2000s. There's a chapter here in this intro to focused ion beams, which discuss this. But the idea is to prepare a fib specimen such that it is retained inside of the trenches, and then you move the sample outside of the fib onto a standalone micromanipulator station with a optical microscope so that you can see where the specimens are and how to then be able to pluck them out. So the paradigm shift is basically, at what point do you do lift out? Many people might be familiar with the so-called in situ lift out technique. With in situ lift out, there is a probe that is mounted either inside of a fib or on the chamber wall of a fib. This requires that the probe be inserted and the probe be somehow attached to the specimen, or using grippers grabbing the specimen. And then it also requires the sample to be attached to a suitable grid, and then the probe itself to be removed from the sample. And these are all the steps in red. So the general steps for fib specimen preparation for in situ lift out and for ex situ lift out are essentially identical, with the only differences being how you get the specimen itself to a suitable grid carrier. And it is well known, there's no secret here, that it can take several minutes, up to tens of minutes, up to hours for some users to do in situ lift out, compared to less than a minute or just a couple of minutes for ex situ lift out. And so the speed is not disputed. We have been able to apply ex situ lift out techniques to a number of different specimens. And early on, we were interested in fib milling different sample types. And now, of course, we can even make or use a plasma fib for different samples. So anything from polymers to ceramics, metals, even hard biological type samples like bone. Here, this is an example of nacre, abalone, composites, thin films, etc. And they can be used for conventional TEM as well as high resolution TEM. And so it was quite fortuitous that early on, when we were interested in applying FIB to TEM specimen prep, that ex situ lift out also worked for a variety of samples. And the reason is, if you take a look at adhesion forces at very small scales, you find that adhesion forces are proportional to surface area. And back early on, we thought that the ex situ lift out technique was primarily due to electrostatic forces. And actually, if you take a look at these adhesion forces, you see that the large contribution of the adhesion forces is actually due to the van der Waals forces. And if you plot a log scale of force versus fib specimen length, you can see this very large 10 to the 12 to 10 to the 15 orders of magnitude force over, for example, the force of gravity. Oops, sorry, there's an automated timer on that slide. The only material constant in this equation is this so-called Haymaker constant, and this varies only 2 orders of magnitude over the entire periodic table. So if you even subtract 2 orders of magnitude off of this van der Waals force equation, you see that you still have an extremely large contribution of the van der Waals forces with respect to this, with these sizes, with respect to these surface areas. And so this is why this technique works, and this is why it actually works extremely well. We actually learned over the years that it is also beneficial to totally eliminate electrostatic forces. And the way you can do that is to metallize the tip. So we use glass probes that are pulled to a fine point, about a micron in size. And with these tips, we're using, again, the surface area of the rounded edge of the tip. We are not poking at the sample. We are not spearing it. We are not embedding the tip into the sample. We are just using the side of the surface area of the tip to just touch the specimen. It clings to the probe via electrostatic forces, and then we can easily manipulate the specimen to, in this case, a carbon-coated TEM grid. There's a number of reasons why we use glass tips instead of, for example, tungsten tips, which are already, of course, metal and conducting. The main reason is because if anybody has done in situ lift out and has accidentally doinked the tip onto the specimen, you know that those tungsten probes are extremely ductile and they will just curl up like a little elf shoe. So the glass tips will bend and deflect without breaking in most cases, and so you can fish around the trench for the specimen without having the tip break. And by either coating the tip with, for example, hobby ink or in a spotter coater, we can metallize the tips, and we found a lot of success doing that. So the bottom left shows a movie that's been sped up, but what you see there are 0 minutes. Those are seconds and milliseconds, and this movie is going to just repeat. It's just sped up a little time. And above it, you see the timestamps. And this is the time for manipulation to laying down the specimen onto a carbon-coated grid. And you see this is done in about 28 seconds. These specimens can be manipulated to either a wholly carbon grid, a carbon-coated grid. We have these patented grids. These are half grids. With shapes that allow the specimen to rest on the grid itself without any carbon support across it. This allows you to post fib mill the specimen. If the specimen's too thick, you can put it back in the fib. You can put it in, for example, an argon ion mill, etc. And we have done lift out competitions at microscopy and microanalysis now for a number of years, where over the course of a show have lifted out more than 60 specimens on the show floor. This would be extremely difficult to do with in situ lift out. And our competitions also consist of both novice division and veteran division, and even novices can be taught to do this technique in a matter of minutes. And in this case, from 2023, we had a winner do it in just a minute, and we had a veteran do it in 54 seconds. At M&M 2024, we actually operated our system completely remotely. So we left our system in Florida, and we used complete remote operation and followed up with a contest that way. So the old perceived limitations of ex situ lift out were completely resolved. We don't have to worry about a carbon film. We can put samples on these patented slotted grids, and we can post thin them. We can even do argon ion milling, for example, and we can make very, very thin specimens for high resolution microscopy. We also offer a number of different grid materials. We can offer nickel. So for EDS applications and materials, ideally, you want to use a grid for quantification, for analysis, that is not a component of your sample. So we can offer copper grids, nickel grids. We offer half grids, full grids, and we also offer what we call express low Z grids. These are low atomic number grids. These are made of nanocrystalline diamond. The advantage to these grids is that this reduces any EDS overlaps, because the grids, basically you just get a carbon signal. So this reduces fluorescence of the grid itself and also reduces the background bremsstrahlung from the EDS signal. The one other thing that we have also developed are these practice 3D printed specimens, which are called praxis. Praxis is actually Latin for practice. And these specimens allow us to teach and train users not only how to do ex situ lift out as shown here on the right, but theoretically you can also teach people to do in situ lift out as well. And in fact, it was these specimens that we used to first qualify and show that cryo ex situ lift out was possible. So let me continue on then, and that gives you a little bit of background of what ex situ lift out is and how it can be used. So why would this be beneficial for cryo ex situ lift out? Obviously, it's just like any other, we're doing lift out just like any other fib technique. And again, this technique is fib agnostic, so you can use any fib and any TEM since this is done outside of the fib. There's no reason why it can't be used with correlative microscopy as well. It can be used on plunge frozen or high pressure frozen samples. It is faster and theoretically faster and easier than cryo in situ lift out. And then you're not using an expensive fib to do the manipulation process itself. And all of that leads to higher throughput, lower cost per specimen, and quicker time to data. So thus far, we have a number of publications. Our second publication here, which I'll talk about on the heat transfer, was selected for cover art for microscopy and microanalysis earlier this year, and we also have a patent on this. So this work was proposed for a phase 1 DOE grant. We have just wound down our phase 2 grant. We have an additional manuscript coming out, which I'll talk to you about today, some of the data. And we also have one manuscript in review on some of the data that you'll see today as well. So we've been working with our partner at Cornell University for the past several years. Unfortunately, the very sad and premature passing of our collaborator, Dr. Lena Kokrudis, happened a couple of years ago. We've continued to work with Cornell on this, but Lena was instrumental in allowing us access to her lab during COVID when we first started to do this. But basically, the cryo version of the cryo ex situ lift out solution um, consists of putting our ambient system, if you will, inside of a glove box where we can contain relative humidity. And because we have since motorized everything about the system, is once we load our samples, and I'll show you how we do that, onto the stage of our lift out tool, we can run everything outside of the cryo box remotely. So one of the first things we had to do, or in conjunction with the experimental, we had to make sure that the geometry of a cryo ex situ lift out fib specimen would remain vitreous. And so our partners at Center Corp, Kyle Beggs and Alan Kassab, worked with us to do heat transfer analysis of essentially the fib-sem geometry and a cryo stage. This happens to be a quorum cryo stage, which flows cold liquid nitrogen gas into this tubing. This is a cold finger here. This is the stage. You can see that the scale here from red to blue is actually minus 188 all the way down to minus 190 in this case. And so the red color is the warmest, but you can see it's extremely still within or underneath the vitreous temperatures. And this is the boundary radiation heat flux. And so you can see that this is the image that became cover art. This is our thin specimen, and what this shows actually, and as we go to the next slide, we can see that if we alter the size of these remaining tabs of the specimen, again, the red to the blue is a little deceiving because this is only a couple of degrees C. But you see that the warmest part of the specimen is going to be at the part where that has the thinnest amount of material. And this shows time to critical temperature as a result of cross-sectional area. But what this shows is that as long as the specimen remains touching to any part of the trench wall, it will remain vitreous versus via conduction. And so this shows that the fib methods itself in producing a cryo ex situ lift out specimen will in fact theoretically work. Okay, so we can make our fib specimens that are very similar to our conventional ambient fib sample under cryo mode. We developed a special cryo holder that can go on top of a, in this case, quorum dovetail that has an anti-frost lid. And when we pull it out of the prep chamber, we developed or we had a cryostat inside a vacuum transfer system. So we can take the specimen, cold specimen, put it right into this little cryo jacket, and then remove the holder, put a lid on it, pump vacuum, so that we can take it into our cryostat. This is what it looks like from the top down. This is our cryostat filled with liquid nitrogen. We have our cryo shuttle holder that comes out of the fib. This cryo jacket keeps everything cold through conduction, but there's no liquid nitrogen inside the cryo jacket. This preserves the fib specimens. And then we have something which we call the little moat support, where we will, once we get it inside the glove box, position the cryo holder on top of the moat support. So this is what it looks like. We then carry it into our glove box uh, load lock area. The glove box itself can be backfilled, and typically we backfill it with nitrogen. It could also be backfilled with argon. It needs to be less than 10% relative humidity. And then once inside, we disassemble it. We can put it then onto the lift out station, and we can basically start the lift out process. So we pull the sample holder out of the jacket, place it on top of this little moat support, and then all the manipulation is done in the cryo vapor phase above the liquid nitrogen level using the microscope. We also have developed cryo transfer for Leica stages. We can do this one of two ways. We're currently testing this. We can do it by just using one of the Leica load locks on top of our vacuum system, or we can just do the transfer within the VCM and VCT. So just to show you that, again, this works via transfer of the system in the cryo vapor phase. We've looked again at the heat transfer. This is a temperature as a function of distance from the cryo holder working surface. And what we can see is that well over a millimeter above the surface, we remain below the vitreous temperatures. And in fact, this liquid nitrogen at this level will last for tens of minutes. And then, of course, there's no reason why you couldn't top this off periodically with liquid nitrogen to keep the level high enough for several tens of minutes. So our first attempt at trying this was with those polymer Praxis samples. So this is an SEM image of the finished fib specimen. Then it was transferred. This is the micromanipulation. You can see the specimen at the end of the probe. This is placement of the specimen onto a C-flat grid, and then we transitioned it into a cryo TEM. We can see a little bit of contamination here during the transfer that fell onto the grid itself. But if we take a close look at the FFTs of both the polymer sample and just the support film itself, we see no evidence of ice contamination in the FFT. So we know then that the transfer process worked and there was no contamination. We have done this also on plunge frozen yeast. And one of the other advantages of this technique, and some of it I think is our fib experience, but we can make also 4 specimens, for example, in 4 hours. We can do this pretty quickly. Here's what the specimens look like after they're completely fib milled free and cut free. They remain touching inside of the trench. We manipulate it to the cryo-exlo station. Here's the specimen on the grid, and then, specimen on the probe, and then the specimen on the grid. Here's a low magnification TEM image. And then, of course, here's our, again, further evidence, higher magnifications and FFTs showing no evidence of devitrification. Turns out that the fib process itself for high pressure frozen samples, whose people that are doing this can attest that high pressure frozen yeast is definitely, or high pressure frozen samples for that matter, is aptly named. These high pressure frozen samples are highly stressed. They're highly insulating. So our first attempt of this was with a high pressure frozen sample with several hundred microns of sample in the middle of a planchette. We had problems with conduction, so we put an extra grid on top of there. We put cryoplatinum kind of deposited everywhere and onto the grid. And we were basically following the method of Kelly to do also this stress relief cut with the fib. And we were able to get a cryo exlo specimen manipulated. Unfortunately, we weren't able to get this sample to the TEM. We have since prepared or gotten specimens prepared by the waffle method. These are definitely a lot easier to work with. We still need to do this so-called stress release cut, and we're working on the transfer of these specimens into the TEM. So just very quickly, we also have alternative workflows for specimens where for specimens that do not need to remain cold or vitreous through the ex situ lift out process, this is extremely easy. We don't have to do in situ lift out cold. So we can do all the cryofib milling in any cryofib. We can do the cryo TEM. All we have to do is warm up the sample and do now ambient ex situ lift out, and this can be done with humidity controlled and backfilled. So if you have beam sensitive materials, air sensitive materials, or sensitive that have to be fib milled cold, such as polymers or other samples, this can be done quite easily. So here's some particles embedded in a polymer, and we were able to do some tomography here and do some particle analysis. This is the additional manuscript that we're working on. This is fib milling of indium metal, so any low temperature metal or low temperature material that is going to be ion beam sensitive or electron beam sensitive. We can do the milling cold, we can do the imaging cold. There is no need to do the manipulation cold, and so this was all done in ambient conditions. Again, additional polymers, and this is an organic, inorganic perovskite with NREL, Nikita, Duda, and Katie Jung-Johan. Just to wrap up, again, the advantage to this is the time savings. It's easier time to data. I won't belabor this point, but to sum up, we've developed cryo ex situ lift out. We can do a variety of different workflows for materials that, for example, don't have to remain vitreous. I'd like to acknowledge collaborators both at Expresslo, Cornell, PNNL, Centocorp, and Andy Imes, who's now at NIST, and of course, in memoriam of Lena Kirkudis. And some final comments. Thank you, DOE. We can make custom holders. The big thing I just want to mention is for those people doing cryo. So 10, 20 years ago, people doing TEM got really concerned about their room, acoustics, laminar air conditioning, etc., temperature stability. I think we really need to start thinking about adding relative humidity requirements to room. Even in upstate New York, doing or attempting to do cryo work in the summer months is a complete waste of time. Really difficult to do. So it's just something to think about.